SpaceX's metal heat shield test on Flight 10 failed so badly it turned half the rocket orange with rust. VP William Gersten-Meyer just revealed why they're abandoning this approach entirely. But here's what's really happening. This disaster is actually leading to their most promising breakthrough yet. What did they discover that changes everything? Picture this. August 26th, Flight 10, Ship 37, screaming through Earth's atmosphere at 25,000 kilometers per hour. SpaceX engineers watch their screens as something unprecedented unfolded. 6 tiny metal tiles were about to create the most visible failure in Starship's history, turning half a 52-meter rocket bright orange with rust. Here's what actually happened during those critical minutes, and why it represents one of the most expensive learning moments in aerospace history. When Ship 37 hit 120 kilometers altitude, atmospheric compression began generating plasma temperatures reaching 2,000 degrees Celsius. Those 6 experimental metallic tiles, just 3 on each side among thousands of ceramic counterparts, started a chemical reaction that aerospace engineers had feared for decades. But there's a detail most people completely miss about this spectacular failure. Unlike SpaceX's proven stainless steel 304L construction, which survives re-entry thanks to protective chromium oxide layers, these test tiles likely contained higher iron content with thinner chromium protection. The moment they encountered atomic oxygen in the thermosphere plasma, oxidation accelerated thousands of times beyond normal atmospheric rates. Think of it like throwing iron filings into a blowtorch, except this blowtorch was moving at Mach 25 through an environment that doesn't exist anywhere on Earth. William Gersten-Meyer, SpaceX's VP of Flight Reliability, revealed the devastating technical details at the Glenn Space Technology Symposium. Basically, we were testing whether we could use non-ceramic tiles. We put 3 metal tiles on each side of the rocket to see if they could handle the heat. It turned out they just couldn't. The engineering nightmare gets progressively worse when you understand the physics involved. When metals oxidize under extreme heat, the resulting rust layer expands at different rates than the base metal beneath. This thermal expansion mismatch creates stress fractures that cause the oxide coating to crack and flake off like old paint peeling from a house. And here's what few people realize about the visual spectacle everyone witnessed. The high-speed plasma flow then carried this loose rust powder along Starship's hull. Combined with the vehicle's high angle of attack during re-entry and humid ocean air at splashdown, it created that unmistakable reddish flow streaking down the rocket's body, almost as if rust were literally melting into water. But here's the truly staggering part that demonstrates the scale of this failure. If just 6 metallic tiles could stain half the rocket's belly bright orange, imagine covering the entire vehicle with thousands of them. The corrosion would occur on a massive scale that could compromise structural integrity. The irony runs deeper than most people understand. NASA experimented with metallic heat shields back in the 1970s, but those tests never progressed beyond laboratory conditions. SpaceX's real-world experiment essentially confirmed what aerospace engineers suspected for 5 decades. Metallic heat shields face fundamental physics problems that can't be solved simply with better alloys. And here's what's truly noteworthy. SpaceX knew this was a high-risk experiment from the beginning. They deliberately flew hardware they suspected might fail spectacularly because laboratory testing couldn't replicate the extreme conditions of Mach 25 re-entry. But this is just the beginning. What's really surprising is how this visible disaster simultaneously revealed their most promising breakthrough yet, hidden in plain sight during the exact same flight. This leads to a remarkable discovery that most space industry analysts completely missed while focusing on the dramatic rust staining. While everyone watched that orange disaster unfold, SpaceX was simultaneously running a second experiment that revealed something far more valuable than metallic tiles ever could have provided. And this is where the real story begins, because what looked like comprehensive failure was actually accelerating their development timeline in ways nobody anticipated. During the same Flight 10 re-entry, engineers noticed white patches appearing near Starship's nose, where ceramic tiles had been deliberately removed for testing purposes. This wasn't accidental damage. It was strategic data collection that provided crucial insights into heat shield performance under real-world conditions. But there's a detail most people overlook about these white patches that changes everything we thought we knew about spacecraft heat protection systems. The white residue came from Dragon spacecraft heat shield material positioned underneath Starship's ceramic tiles, being systematically eroded by plasma sneaking through gaps between individual tiles. Gersten-Meyer explained, heat was essentially sneaking into the gaps between tiles, working its way underneath and eroding that secondary layer as well. This discovery revealed a fundamental problem that has plagued every reusable spacecraft since the shuttle program began. Gap infiltration isn't just a minor maintenance issue. It's the primary reason why spacecraft turnaround takes months instead of days, making true reusability economically questionable. And here's what's truly remarkable about this moment. In the middle of these problematic white patches, something extraordinary appeared. Dark areas where ground crews had installed experimental material called crunch wrap. Here's why this changes the entire reusable rocket industry landscape in ways that extend far beyond SpaceX's immediate goals. Traditional heat shield maintenance represents the difference between space access, costing $10,000 per kilogram, versus $100 per kilogram. Every ceramic tile requires individual manufacturing, precision installation, inspection, and potential replacement after each flight. Gap fillers add another layer of complexity. They're difficult to install, sometimes pop out during flight, and require extensive inspection between missions. SpaceX's crunch wrap approach eliminates these problems through elegant engineering simplicity. The material functions like engineered shrink wrap around each ceramic tile, mechanically pressed into position by robotic systems rather than adhesively bonded. When technicians install tiles, the brittle wrap material sits around tile edges. Then excess material gets trimmed away at the surface level. But there's something most people miss about this breakthrough that connects to broader competitive dynamics reshaping the space industry. While Blue Origin's New Glenn focuses on traditional partial reusability, in China's space program develops conventional reusable approaches. SpaceX is potentially about to leapfrog everyone with a solution that enables airline-like operational tempo. The economic implications are staggering. We're talking about maintenance cycles measured in hours rather than weeks. The timeline significance becomes crucial when you consider upcoming Artemis missions. NASA needs reliable crew transportation systems for lunar flights scheduled in 2026 to 2027. Traditional spacecraft maintenance schedules simply cannot support the mission cadence required for sustained lunar operations. And here's the detail that connects everything about SpaceX's experimental approach. Their willingness to fail spectacularly in public generates real-world performance data that no competitor can access through years of laboratory testing. While traditional aerospace companies conduct exhaustive ground-based analysis, SpaceX learns faster by flying experimental hardware on actual missions. The competitive implications extend beyond immediate technical advantages. SpaceX is essentially beta testing solutions that could define industry standards for the next decade of space exploration. Every failure provides data that accelerates their development cycle, while competitors remain limited to theoretical modeling. And this is where things get interesting, because what appeared to be SpaceX's most visible setback is actually validating their rapid iteration philosophy in ways that could reshape human spaceflight forever. What happens when you combine the world's most public spacecraft failure with a breakthrough discovery that could revolutionize space access economics forever? You get Flight 11 and potentially the most important validation test in reusable spaceflight history. Here's what's really happening behind the scenes that changes everything about our timeline for routine space commercialization. SpaceX isn't just adding crunch wrap material to Flight 11's heat shield system. They're implementing what Gersten-Meyer calls an anti-rattle layer that addresses the one remaining engineering concern about their breakthrough sealing approach. The brittleness issue that worried engineers about repeated thermal cycling is being solved through redundant protection systems. But there's a remarkable development timeline detail that most people miss. This accelerated problem-solving cycle means SpaceX could validate their comprehensive heat shield solution months ahead of original development schedules. While traditional aerospace companies would spend years analyzing Flight 10 data before attempting modifications, SpaceX is flying their solution on the very next test flight. And here's what's truly noteworthy about this rapid iteration approach. It demonstrates how SpaceX's fail fast, learn faster philosophy is actually shortening development timelines rather than extending them through repeated failures. The implications for upcoming deep space missions are potentially game-changing in ways that extend far beyond Starship's immediate capabilities. NASA's Artemis program requires crew transportation systems that can support multiple lunar missions per year without extensive refurbishment periods. Current spacecraft maintenance cycles simply cannot accommodate this operational tempo. If Flight 11 successfully validates crunch wrap technology combined with anti-rattle protection, Starship becomes the first spacecraft in history capable of airline-like turnaround times for deep space operations. We're talking about maintenance cycles measured in days rather than months, fundamentally altering the economics of space exploration. But there's a broader transformation happening that connects to SpaceX's long-term strategic objectives that most analysts overlook. Consider this progression. Metallic tiles failed because fundamental physics defeated advanced materials engineering. But that spectacular failure revealed plasma infiltration problems affecting ceramic tile performance. This led directly to crunch wrap development, which potentially provides better thermal protection than their original metallic concept could ever have achieved. The economic transformation implications are staggering when you project forward to routine space operations. Current space access costs thousands of dollars per kilogram, primarily due to hardware replacement and refurbishment requirements. SpaceX's breakthrough could reduce these costs to hundreds of dollars per kilogram by eliminating major maintenance cycles. And here's what's truly remarkable about this technological moment. It makes previously theoretical concepts like Mars colonization, asteroid mining, and orbital manufacturing economically viable for the first time in human history. The timeline convergence is particularly significant. SpaceX's IMAP mission launching September 23rd demonstrates their current capabilities, while Flight 11 could validate the technologies that enable their next-generation ambitions. The gap between current operations and revolutionary capabilities is shrinking rapidly. But there's an even larger context that connects SpaceX's heat shield breakthrough to fundamental questions about humanity's spacefaring future. When reusable spacecraft operate with airline-like reliability and economics, space stops being an exclusive domain for governments and billionaires. Commercial space stations, lunar hotels, asteroid mining operations, everything becomes possible when transportation costs drop by orders of magnitude. The irony is absolutely perfect in ways that demonstrate how breakthrough innovations often emerge from apparent disasters. SpaceX's most visible failure on Flight 10 revealed the pathway to solving reusable spaceflight's last major engineering challenge. That orange-stained rocket belly might represent the moment when routine space access became technically and economically inevitable. And here's the most important detail of all. Flight 11 will determine whether we just witnessed the inflection point that transforms space from frontier to neighborhood. In a few months, we'll know if that rust-stained disaster was actually the moment that changed human civilization's relationship with the cosmos forever. The future is about to become visible in ways nobody anticipated, disguised as the recovery from spectacular failure. This is exactly why SpaceX's disaster might be the most important failure in space history. What looked catastrophic actually revealed the final piece of the reusable spaceflight puzzle, proving that breakthrough innovations often emerge from spectacular failures. Here's what this means. We're witnessing the moment space access transforms from exclusive frontier to routine transportation. When Starship achieves airline-like operations, Mars missions and asteroid mining become economically viable within this decade. Flight 11 launches in weeks with validation tests that could confirm humanity just solved the last major barrier to space commercialization. The timeline is accelerating. We could see sustained lunar operations by 2027. How do you think this breakthrough reshapes the space race? Will competitors adapt fast enough, or is SpaceX establishing an insurmountable lead? This is Space Hub, decoding the engineering breakthroughs shaping our spacefaring future. For more deep dive analysis like this, hit subscribe. Sometimes the most important revolutions start with rust stains and brilliant solutions hidden in plain sight.